All right, we're going to start momentum and impulse today. Now, I'm sure that all of you have heard of the word momentum before, used probably in lots of different cases. If any of you are involved in sports, lots of times your coaches will say, use your momentum to gain possession of the ball or the puck. Use your momentum to take the other person off of the ball or puck. But what is it really? Well, if you think about inertia, momentum is connected to inertia. And both of them are connected to the mass that an object has. And that object's desire to keep doing what it's doing. Momentum's letter is P. I don't know why. It's a small p. Capital P is power, but momentum is a small p. And there are two factors that affect momentum: the object's mass and the object's velocity. And really, the equation for momentum is quite simple. It's P equals mv. Mass times velocity. Okay? The units then would be kilogram meters per second. And unlike the Newton, which was kilogram meters per second squared, this hasn't been renamed yet. So momentum is measured in kilogram meters per second. Okay, momentum is a vector, which means it needs a direction. And the direction of the momentum will always be the same as the direction of the velocity, right? Because mass isn't a vector. So the momentum gets its direction from the velocity. It is possible for something that's really, really, really tiny to have more momentum than something big. For example, it's possible for a hummingbird to have more momentum than a school bus. How? I'm waiting for you to think of the how. The reason is, as long as the hummingbird is moving, if the school bus is at rest, then the hummingbird will have more momentum than the school bus. One of my favorite games growing up was called the train game. And in the train game, you needed to be near a set of train tracks, and there needed to be like a station where the train was going to stop up here somewhere. And you needed to know when the train was coming. And so when you knew the train was coming, you stood beside the tracks and you started to run. So that by the time the train got up to you, you and the train were going the same speed. It needed to be near the station because you're only going to be able to go the same speed as the train if the train has already begun to start to slow down. So you and the train are going the same speed, and then the game is to see who will stop the first. It was my favorite game ever. You know why? Because I always won. Why did I always win? Because even though we both had the same velocity, the train has a lot more momentum than I do. Because in case you don't know, the train has a lot more mass than I do. And in order to come to a stop, both of us need to get rid of all the momentum we have. So really, for an object in physics, it's not so much how much momentum an object has, but how much the object needs to change its momentum by. And so if both of us need to come to a stop, it means we need to drop all of our momentum. Change in momentum is equal to mass times change in velocity. Now it's true, if I'm driving down the road in a half-ton truck and the light in front of me turns red, which means I need to bring all of my momentum to zero, it is true that I could try to get rid of some of the mass. Maybe I could put my buddy on the back of the truck and he could throw the pumpkins or the boxes or whatever's on the back of the truck off, trying to bring my mass down. But it's probably a lot easier idea to step on the brakes and bring my velocity down. So change in momentum is usually written as equal to mass times change in velocity. When you go on into university, you'll see some questions where the change in momentum happens because of the change in mass. But this whole point is, if the mass is really big it's gonna take a longer time for the object to lose its momentum, right? If we're both going the same speed but something has a big mass, it's gonna take a lot more time to lose its momentum. It's why you often hear when there's a train accident, you'll hear the conductor say, by the time I saw the car on the track, there was nothing I could do to stop. Because even though they might put their brakes on full force, there's no way they can bring their momentum down to zero because the brakes have a limited amount. Now, if we say brakes, it means that how do you change an object's momentum? Well, you must change it by having to apply a force, right? And so there's something that's called impulse, and it's a J. And so momentum is a P, and impulse is a J. And impulse is equal to F delta T. And in order to change an object's momentum, you need to apply a force over a given period of time. And these two are connected together. How are they connected together? They're connected together through Newton's second law, F equals ma. A, we know, is Vf minus Vi over delta T. If I bring the delta T over to this side, I have F delta T is equal to m Vf minus Vi. Well, and we know that Vf minus Vi is just delta V. So I have F delta T is equal to m delta V. Well, F delta T is J, called the impulse, and m delta V is delta P. And so when you apply an impulse on an object, a force over a given period of time, you end up changing the object's momentum. If J is equal to F delta T and F delta T is equal to m delta V and m delta V is equal to delta P, then they all must be equal to each other. And this comes in handy when you're doing a question. You can pick any two corners. Okay, so momentum, change in momentum, and impulse. All of this explains why, like, airplanes have such long runways. A few years ago, probably 10 now, in Fredericton, there was a large plane that needed to make an emergency landing. It was on its way to Toronto or somewhere, but something was wrong. So it landed at the Fredericton airport. The problem is the Fredericton airport isn't made for large planes to land, and so it couldn't get rid of all of its momentum quick enough, right? There was a certain amount of force happening between the plane and the tires and the runway and the air flaps, so there was only a certain amount of braking force that it had. And it had to bring this down to zero, but because the mass was so big, it needed a fairly long runway. Fredericton Airport didn't have it. It actually went off the end of the runway, across the field, and ended up across the Lincoln Road. Now, they knew it was coming, so they had traffic stopped and no one was hurt. But it's just an example of how when you have a really large mass, you need a lot of time to bring its momentum to zero. It's why you don't pull out in front of a transport truck the way you might in front of a smart car or a Toyota Corolla. Okay? It's also why this F delta T and this change in momentum comes in, it's really important in sports. Think about when you're swinging a baseball bat, when you're swinging a hockey stick, when you're volleying a volleyball or passing a basketball. Your coach always says, follow through. Why? Because I'm maybe limited by the amount of force I need to put on, or I can put on because of my muscles. But if I follow through, I'm increasing the delta T. And by increasing the delta T, then I'm making the impulse that I'm putting on that object bigger. And if my J is bigger, my change in momentum will be bigger. And so the object will be able to go further. Okay? It also comes important when you're driving a car. If you need to bring your momentum to zero, then you can either put a huge force on, I'm going to run out of time.